We're going to determine if the series, the summation n equals 3 to infinity of n plus natural log of n plus sine of n plus 5 divided by 2n squared plus cosine of n squared plus 3n converges or diverges. And we're going to use the limit comparison test, which I'll abbreviate by LCT. Now recall, limit comparison test works like this. Suppose we have two series. One we'll call summation a sub n, and the other we'll call the summation of b sub n, with a sub n and b sub n restricted being positive. If the limit as n goes to infinity of an divided by bn is equal to L, and this limit L is positive and finite, then the following is true. Either the two series, the a sub n series and the b sub n series, can both converge, or the a sub n series and the b sub n series both diverge. We cannot have an converging series and b sub n be diverging, and vice versa. So now we're going to call the summation from 3 to infinity a sub n, the series that we are examining. So it's summation from 3 to infinity n plus the natural log of n plus sine of n plus 5, and then divided by 2n squared plus cosine of n squared plus 3n. Now before we select the b sub n series, let's remember a couple of things. First, ln of x is less than x for, this is true for x actually greater than 0. So this is because natural log is defined for x greater than 0, and whatever we plug in, whatever value we put into the natural log, it will always be less than the value itself. In particular, ln of n is less than n for n greater or equal to 3, because this is where our series starts. And also you have to remember that sine of anything, in particular sine of n plus 5, is always between a 1, less than or equal to 1, and greater than or equal to minus 1. Sine can't be larger than 1 or smaller than minus 1. It's confined to be between those values for anything we put in it. Similarly, cosine of n squared plus 3n is always less than or equal to 1 and greater than or equal to minus 1. So as we examine our a sub n series, we note that in the numerator, as n becomes larger and larger and larger, the n term right here will dominate. And in the denominator, the 2n squared term will dominate for larger and larger values of n. The others will be much smaller and could be neglected when n becomes very, very large. So the selection for our bn series should be done by looking at these dominant terms in the numerator and the denominator. So we see that the highest power of n in the denominator, let's call it d, is equal to 2 because we have an n squared in there. And the highest power of n in the numerator, let's call it n, is 1. And the difference between them is 1. And our selection now for the b sub n series, so it will be n equals 3 to infinity of b sub n, will be the simplest series, so that the difference in powers, denominator minus numerator, is 1. And of course such series is summation from 3 to infinity of 1 over n. Now let's compute the limit as n goes to infinity of a sub n divided by b sub n. And that limit looks like this. We have the limit as n goes to infinity, n plus ln of n plus sine of n plus 5, and divided by 2n squared plus cosine of n squared plus 3n, all this divided by 1 over n. Now this is equal to, that has the effect of multiplying the numerator by n, so this is the limit as n goes to infinity. We get n squared plus n times natural log of n plus n times the sine of n plus 5, and divided by 2n squared plus cosine of n squared plus 3n. Now to evaluate this limit, we're going to now divide everything in the numerator and denominator by n squared, because it's the highest power of n that we can find. So this is equal to limit n goes to infinity, n squared over n squared is 1, plus ln of n over n, plus sine of n plus 5 divided by n. And we do the same thing in the denominator. 2n squared over n squared is 2, plus cosine of n squared plus 3n divided by n squared. Now all we have to do is compute these individual limits and we'll be done. So first limit we're going to compute is the ln of n over n, the limit as n goes to infinity of ln of n over n, and that's equal to the limit as x goes to infinity. We pass this on to continuous function ln of x over x. We get an indeterminate form, infinity over infinity. We apply the L'Hopital's rule, and that's the limit x goes to infinity, 1 over x over 1, which is equal to 0. So this limit here that I'm circling, this is heading towards 0 as n goes to infinity. Now let's look at the two limits involving the trigonometric functions. The first limit is the limit as n approaches infinity of sine of n plus 5 divided by n. But note that sine of n plus 5 divided by n is less than or equal to 1 over n and greater than or equal to minus 1 over n, because sine of anything is between minus 1 and 1. So now using the squeeze theorem, we have the limit as n goes to infinity of sine of n plus 5 divided by n less than or equal to limit n goes to infinity 1 over n and greater than or equal to limit n goes to infinity minus 1 over n. Now clearly this is heading to 0, this is heading towards 0, and this limit is also heading towards 0 by squeeze theorem. And we apply exactly the same thing to the cosine term, that is the limit as n goes to infinity of cosine of n squared plus 3n divided by n squared is less than or equal to the limit n going to infinity 1 over n squared greater than or equal to the limit n going to infinity minus 1 over n squared. Once again, the limit on the left side going to 0, the limit on the right is going to 0, and by squeeze theorem the limit in the middle is also going to 0. Now our limit is just going to be the constants that we have. So this, let's return to our limit. Our limit was limit as n goes to infinity, and we had n squared plus n times natural log of n plus n times the sine of n plus 5, and this was divided by 2n squared plus cosine of n squared plus 3n. And once we simplified it, we know that the limit will be 1/2, which is our L. It is positive, it is finite, and therefore we can now make the following conclusion. The series summation from 3 to infinity, n plus the natural log of n plus the sine of n plus 5 divided by 2n squared plus cosine of n squared plus 3n, and the series n equals to 3 to infinity of 1 over n behave the same way. That is, either they both converge or both diverge. Now the series from 3 to infinity 1 over n, it's not exactly harmonic series because harmonic series starts at 1, but we can think of it as a harmonic series minus the first two terms. So this is basically harmonic, and we know that the harmonic series diverges. And because it diverges, we can now conclude that this more complicated series with n plus ln of n plus the sine term in the numerator and 2n squared plus the cosine term in the denominator also diverges, and this is by limit comparison test. For more videos, visit www.mathprepvideos.com.